Okay, I'm going to talk about um, one kind of integral. Uh, uh, I don't really need to give this a name, but I'm just going to call this the exponential integral, and it's going to be in spherical coordinates. And the reason I'm giving this a name is that this has a physical interpretation. First, let me just draw the integral. It's the integral over our region of e to the a times the square root of x squared plus y squared plus z squared times the volume. And E will just be enclosed by, say, the unit sphere. So if I just briefly sketch this on the RZ plane, then on the XY plane, then that's what this region corresponds to. Okay, now the fact that we have sums of squares, that immediately leads us to want to integrate this in spherical coordinates. We also see the sums of squares in the integrand, so immediately you should think of spherical coordinates. And you see immediately that e to the a times rho, that's what the integrand will look like in spherical coordinates. We'll also have our usual rho squared sine phi d rho d phi d theta. And you can see that there's no other theta or phi dependence, so this will actually be it will factor. And so it'll be quite a nice integral. So why am I talking about this thing? It doesn't seem that special. This actually has a very strong physical interpretation. This is the lowest energy state of the hydrogen atom. The hydrogen atom. So if you have a proton and electron, then the electron will actually, what it does not do is it does not orbit around the proton. What it can exist anywhere. It can exist anywhere in space, but it'll be clustered in around regions which are high likelihood. So if I drew the probability of finding the electron as a function of rho, what it would look like is something like this. And this would be the usual Bohr radius. So you would say it's most likely to find the electron at this point, but really it could exist anywhere. And so if you observe the electron repeatedly, you'll find it in different locations, but it will be clustered heavily around this point here. Okay, and so the probability density of finding an electron is this exponential. It turns out it's e to the minus c rho, where c is some constant that you don't need to know. And there's another constant in front. The values of the constants are not important for this discussion. The point is that finding the integral, so the integral of the probability density, it equals the likelihood of finding the electron in E. So in this case, E is the unit disk. So on this diagram here, it would correspond to integrating the area under this curve. And if you just look at the radius. But I mean, this is a three-dimensional thing. This is just a 1D simplification. But that's the point. And so if you take physical chemistry, biochemistry, or just physics, you'll do integrals of this type to find out the likelihood of finding an electron in a region in a practical experiment. Okay? So I would say this is probably one of the more significant integrals you see in this class. Okay, so how to actually do it? So remember the region is rho less than or equal to 1. On the ZR plane, it was just this circle of radius 1. Okay, so what you do is actually, this is a little too easy. Why don't we just say in the first quadrant? Just to I mean, this is an integration class, right? So we should at least do some slightly more challenging integrals. Um, so let's say also in the first quadrant or octant or whatever. So if we look at the first octant, that means we exclude negative z values. And if we also draw the xy plane, then we exclude theta is larger than pi over 2. Okay, so our rho goes from 0 to 1. Our phi goes from our phi goes from 0 to pi over 2. That ensures we stay in the first octant. And our theta also goes from 0 to pi over 2. Okay, so that means our integral will be, remember, we have constant limits, so we can do it however we want. If you had variable limits, you would stack them in such a way that the functions go on the inside and the constants go on the outside. But I'm just going to put theta here, phi here, and rho here. And then I will put the limits where they need to be. And I'm going to put the same integrand, just put it in spherical. So it was e to the a times rho, and then our dv, which is rho squared sine phi d rho d phi d theta. And now we can factor this as 0 to pi over 2 d theta. Next comes our phi integral, which is 0 to pi over 2 sine phi d phi. And finally, the integral from 0 to 1 of e to the a rho squared d rho. This is our integral. Not so bad, right? I'm just going to talk about this last part. So I'm going to call this now an aside, because this is not needed. I'm going to teach you a skill which is useful in upper division courses and in graduate school, or engineering, or whatever career you do. Yeah, this will be this is something that in very many cases will simplify integrals quite a bit. This is called differentiation under the integral sign, if you are interested enough to look it up. And it basically says do derivatives to evaluate integrals in parameters to evaluate integrals. And the reason this is optional is that you can evaluate, it's a substitute for integration by parts. Which can get rather cumbersome at times. And so this technique is, I think it's pretty awesome. I think the first, I don't know if he was the first one, but if you may have heard of Feynman. He was that famous physicist, Nobel Prize winner. He used this trick a lot to simplify Gaussian integrals. And you can use this. I wouldn't say it's the best technique here, but I think this is a good place to introduce it. So if we recall what our integral is, it's 0 to 1 of e to the a rho squared d rho. how you would evaluate this is by integration by parts. However, what another way to do this is to embed this in a simpler integral. So I'm going to call I of a the integral from 0 to 1 of a similar integrand. But now there's going to be no rho squared. The rho squared is what makes this difficult. So you just remove that rho squared. Okay? So this integral is easy. This is 1 over a e to the a rho from 0 to 1. So this is 1 over a times e to the a minus 1. So now, I prime of a, if you differentiate in a, I know this is kind of weird, right? Because a is not really a variable, it's a parameter, but it works. So let's see what happens. 0 to 1, there's no a's in the limits. So now you just differentiate e, so you get rho times e to the a rho d rho. So now every time you differentiate, you add a rho. So if you differentiate twice, you'll get the rho squared. That's the idea. And so now we've somehow converted integration into differentiation. So now you just differentiate the right-hand side, and that gives you the explicit values you want. So I'm just going to use the product rule. So minus 1 over a squared times the thing on the right side. Now times 1 over a, plus 1 over a times the derivative of the other thing. Okay? So now we just do this one more time, and then we get exactly what we want. So I prime prime of a equals the integral from 0 to 1 of rho squared. That's what we want. Rho squared e to the a rho. That is, we call this thing j up top. This is j. So once we get this, we're done. So now we just do one more derivative. The derivative of the stuff over here. So again, if you use product rule, I'll differentiate the first 1 over a squared. That gives you 2 over a cubed times that e stuff. Now differentiate the e stuff. Minus 1 over a squared times e. Okay, nearly done. Now minus 1 over a squared times e. And now plus 1 over a times e. So let me see if I can simplify this a little bit. I guess you can call this a 2. You can group these two terms here and call that a 2. Minus 2e to the a over a squared. Okay, I don't think we can do much better than that, but that's fine. All we want is the value. We don't need the value to be good. So that means we conclude that our integral is something like 2 over a cubed ea minus 1 minus 2 over a squared e to the a plus 1 over a e to the a. That's it. Okay, so we didn't have to do any integration by parts. So no integration by parts required. We did have to do derivatives, but I think derivatives are a little better. So now, on the homework, a typical homework problem will not have a parameter, but there's a nice trick. So let's say you did something very similar, but you ended up with this integral. Integral from 0 to 1 of e to the 2 rho. No, in fact, let's make it even less obvious. Let's just say e to the rho squared d rho. What do? There's no parameter. Just add a parameter. Then set a equal to 1 later. So let's just compute the integral from 0 to 1 of e to the a rho times rho squared d rho, just the thing we did already, then set a equal to 1. Okay? That's a perfectly legit thing to do, because whatever we get, when you plug in a equals 1, you should get what you want. Okay, so just embed this integral in a parameter problem, then do the parametric, and then do the differentiation under the integral sign, and you can make the trick work. This is something that shows up. I would say not. I would say it's most useful when this upper limit is infinity. So if this is infinity, very, very useful. And you can think about it from the integration parts point of view because the boundary terms will vanish. And so this technique is used for mostly for Gaussian integrals. Because you can integrate things like x squared e to the minus x squared dx. Really what you do is you just add an a in there, and then if you differentiate e to the minus ax squared, that gives you that x squared. Okay? So this is a very useful trick to know. So it's not strictly speaking required, but I'm hoping that it'll enrich your integral suite. Okay, thanks for watching.